Hello, my name is James Liu, and I'm a principal AI scientist at Genentech. Today, it's my pleasure to present this work we've done using Wolfram Language to implement neural PKPD modeling. I will first give an introduction as to why we are using neural nets to build PKPD models. Then, I'll get into how we are using Wolfram Language to implement this. In particular, I will show how Wolfram Language enables model construction in a sequential approach. Firstly, I'll discuss neural PK model, whereby we aim to predict pharmacokinetics from dose. This will be followed by neural PKPD modeling, where we aim to predict PD in relation to PK. We will then compare the model performance with an existing state-of-the-art model and draw some conclusions from the result and the potential next steps. Before we look at the model, let's first look at the kind of data we are trying to model in the PKPD context. The data is in a tabular form with columns consisting of time, the PK measurements, the platelet measurements as the PD variable of interest, and the dose amount. And the missing values in the table have been replaced with -100. Below is a plot of the sample data, where you see dose on the top row and PK and PD on the middle and bottom row, respectively. So currently, how do we go about the process of going from data to model? We use the power of the human mind to abstract data. Namely, we make use of concepts and mechanisms from which we write down equations and parameters. Eventually, after a few iterations, we are then able to capture the observed data and represent it in the digital realm. With the advent of deep learning, we now have another possible paradigm before us. Namely, machines could generate models expressed not as equations, but as neural nets. Our work in applying this concept to the PKPD modeling context using Wolfram Language implementation was published earlier this year in Nature Machine Intelligence. And if you scan the QR code below, it will take you to the article. For the task of data abstraction, we can use an encoder. And the task of the decoder is to reproduce data or make predictions. And you might ask, why are we interested in this modeling 2.0 paradigm? And this is due to the fact that we have growing data complexity, as well as growing needs to develop more medicines tailored to patients who are most likely going to benefit from them. Here, we'll be building the neural net in sequence, first starting from the PK model. The ODE system for the PK model can be expressed as the following, where the aim is to find F, or the vector field, that enables base prediction of the future data. We now look at how the PK vector field is represented using neural network. Firstly, we need to determine the dimensions that we would like to use. The neural network, as you see here, can be simply constructed with net graph. Firstly, we specify the component layers that are involved. Subsequently, we then describe how the layers are connected to each other. And this is done with a very intuitive syntax, as one might be familiar with from graphs. And the information command offered by the Wolfram language is very handy, as it can easily show you the connectivity of the components, as well as how many trainable weights there are in the model. So they serve as a very good sanity check on the model being constructed. Since we are trying to solve an ODE system, we need to choose a numerical integration scheme. For simplicity, we went with forward Euler scheme, where with the step size delta t, the state y at t plus delta t is given by this equation that you see here. And this equation can be implemented quite compactly with Wolfram language and the results visualized. So the code for this is shown here. In particular, the layers for multiplication by delta t and addition can be implemented with element-wise and straight-in layers, respectively. So, as we see here, we can pretty quickly build up desired computations with these existing layers. Note that at every time step, we add in a dose amount, with dose being 0 if it's not been added. Of course, in solving an ODE system, we don't just apply Euler's step once, but many times until we've reached this desired stopping time. And in Wolfram language, we can do this simply by using the NetFault operator. Namely, the new state is fed back into the previous state. In addition, we can specify an initial condition by wrapping that in a net graph. Once we have built this model, we can very readily test out this on a simple set of inputs. In this example, I have taken an initial state of zeros and the PK parameter being a list of ones. And by using a set of 4 doses, 0, 0, 1, 0, this is the output we get, thereby showing that the network is performing as we would have expected. We now move on to the encoder part of the network. Here, we have a sequence of inputs of arbitrary length. For each element of the sequence, we wish to apply a nonlinear transformation represented by a simple feed-forward network. And this can be nicely carried out using the net map thread operator on a net chain. So the complete encoder network is shown here. After passing through a preprocessor, the data goes into gated recurrent layer, which computes and returns a sequence. We then add an attention mechanism to the sequence of outputs from the GRU. As you see with Wolfram language, this encoder can be built with ease. Furthermore, the results can be visualized to check whether or not the model that has been constructed is as we intended it. Finally, before we can train a network, we need to specify the loss function. And there is quite a lot of flexibility offered by Wolfram language to specify pretty arbitrary functions. In this particular instance, we have used the L2 loss with weights. As our data has both PK and PD columns, it's easy to extract the columns relevant to the PK model here by a simple application of path layer and net map thread operator. Finally, after defining the submodules, we see how easy it is to put them all together. And this network is now ready to be trained. In our approach of sequential construction, Wolfram Language offers a handy function, net extract. Indeed, having trained the PK vector field net, we can simply take the relevant part for further use. And now, our task is to build the PD component, which we do following a similar recipe as for the PK, namely by first specifying the dimensions of the network and then construct a net graph. So this network is visualized at the bottom of this plot here. Then it's time to plug the PK and PD submodules together. And one can do this by ensuring causality relationship of PK driving PD is preserved and not the other way around. Visualized below is the network that we have constructed using the PK and PD submodules. In a similar manner to before, the Euler stepping scheme can be performed for both PK and PD simultaneously. All the set of operations required can be built simply from existing network layers. And finally, we wrap a NetFault operator to the Euler step net as previously demonstrated, so as to repeatedly apply the network to steps through time. For the PD encoders, it's largely similar to the PK encoder, so I won't go through all the details. One aspect that's different from the PD encoder is that the initial condition needs to be estimated with a neural net. And this is in contrast to the PK scenario, as there, the initial condition is simply a vector of zeros. Here, the novelty lies in the use of a bidirectional network, namely by applying the net bidirectional operator to a GRU. And one can see how easily this can be done in a Wolfram language. Finally, the neural network for estimating the PD parameters is very much similar to what we have seen before. One aspect that's worth pointing out is that we need to extract the right columns from the data to feed the network so as to be concordant with the PKPD assumptions that we are making. To complete the model, we again need to define the relevant loss function. And certainly a nice thing about the Wolfram language framework is that a rather complex network can be built in a hierarchical manner with each submodule consisting of several components, some of which can be copied from existing trained network. In testing out this methodology, we've taken longitudinal platelet response from more than 600 patients treated with the drug TDM1. Namely, we split the data into 80% trained and 20% test set and apply data augmentation onto the training set to get more than 2,600 records that is then fed into the neural network. Our proposed neural PK-PD model can reproduce the qualitative aspects of the dynamics of a gold standard PK-PD model constructed by my colleague Brendan Bender. In particular, the solid lines are from the neural model, which show similar behavior to the dashed green lines. In particular, both models demonstrate the characteristic decline and recovery after each dose. We can also try to better understand the model dynamics with visualization. Here, we are looking at the trajectory of the system in the 3D phase space. In particular, we examine how the predicted PK and PD variables change with time, as well as a latent state that is described by the model but is not directly measured. Furthermore, we look at the level of activations within layers of the vector field for the encoder. And this is what determines the system dynamics. In the two plots below, we're just looking at the state trajectory from the different angles. And when we see the simulation in action, we note that the latent state goes from an initial high value to gradually lower values. And the jumps that you see in the PK correspond to the times that the patient is dosed. And we certainly see a dynamically changing activation of layers within the decoder on the upper right. So you might ask, how does neural PKPD model perform for making individual patient predictions? The row at the bottom shows the neural PKPD results. We took the same model and considered the following three cases, observing only cycle 1 or cycles 1 and 2, or data from cycles 1 to 3. And in each case, we plotted the unseen data on the horizontal axis and the model predictions on the vertical axis. And we use R-squared and RMSE to measure model predicted performance. And as expected, the more data we use, the better the predicted performance as we go from the first to the last column. In each case, we can compare the gold standard population PKPD model against the neural PKPD model and show favorable performance. Neural PKPD can adapt to emerging data and improve its predictions. Here, we are showing the model predictions. On the top, the solid lines represent the PK and PD predictions. And we see this being updated as individual patient data is fed into the neural network. The visualizations that you see below represent the outputs of the neural network layers from the PK as well as the PD encoders. And as we see this prediction being updated, we note that the individual patient data is being utilized as the observation window, as denoted by the moving line, is moving to the right. And as more data is collected, the prediction becomes better. And we can also see that prediction does stabilize as a lot of data is collected, thereby demonstrating the stability of the encoder in terms of extracting the right information that represents the patient data. One key use of PKPD models is the simulation of alternate dose schedules that the patient may not have been treated with. This left panel shows the prediction range if all the more than 500 patients in the training set were given Q3W, namely once every 3 weeks. So we see the median and 91st percentiles in the left panel. We then simulated what would the PKPD profiles look like if all these training patients were given 1.2 mg per kg at Q1W instead. And we compare the model prediction to the around dozen patients who were given that dose and schedule. And as we can see in the middle panel, there is a fairly good consistency. Finally, we show the model can also simulate a totally untested dose and schedule, namely Q3D, that was never in the training set, thereby showing the ability of the model to generalize well. So hopefully through this talk, I've conveyed to you how Wolfram Language provides high-level functionalities as well as flexibility so as to enable the construction of a novel neural PKPD model with ease. As compared to other deep learning frameworks, the ease with which one can extract, combine, and train only part of the model enabled us to come up with a way to build PK and PD models in sequence. I believe there is a lot of interest amongst scientists and engineers to apply deep learning to dynamical modeling. If there is a layer, neural ODE layer, that enables one to use various underlying ODE solvers, I believe this would find much utility. And finally, I would like to acknowledge my colleagues and collaborators, as well as Wolfram Research for the opportunity to present here. I will be happy to take your questions during the Q&A session, and thank you for your attention. Thanks everyone for joining the presentation and coming to this Q&A session. So are there any questions from anyone? You can either type into the chat box or raise your hand. Okay, I'm getting a question from Robert. So he asks, how are the number of compartments for the PK part of the model handled in the neural network? So yeah, that's a good question. So in this particular implementation that we have, it's kind of following the paradigm of the more traditional population PK modeling approach, in that we have a single compartment. Basically, well, there are multiple species be modeled. In this particular instance, we assume that the model can be described by a system of two ODEs, and that there is a measured compartment, and we divide the model predicted state variable by the volume of distribution. So certainly this dimensionality can change. And one of the benefits of using kind of neural ODE-based approaches is that one can leverage all the existing experience the model has regarding what is the size of the model that may be needed to describe a certain set of data. So this kind of experience one can leverage in this context as well. And we know that from the traditional population PK modeling paradigm that around 2 or 3 state variables may suffice for most data sets, and between 4 to 6 variables for the parameters for each individual patient suffices as well. So of course one can go beyond that, but definitely I think here the modeler can come with his or her own prior experience, intuition as well. Hopefully that answers your question, Robert. Any other questions from the audience? Okay, yeah, so we have another question from Robert. So a very good question regarding, so he asked, what about IV, so intravenous versus oral administration? Yeah, certainly that's a very good one. So definitely, when we have different routes of administration in the typical population PK modeling, one will have different compartments in that context, and certainly we do have quite a lot of data as well, where we have both IV or subcutaneous and oral and so on. So one would have to also, in those contexts, if let's say we have data set that has both subcutaneous and IV, one will have to handle the dosing into these different compartments appropriately. So yes, indeed, there one would have to consider, let's say, for IV dose into one, with your dosing being entered as a vector of zeros with one corresponding to the variable that is representing IV dosing, and in the other case, a vector of 0 except 1 for where the patient corresponding to the subcutaneous compartment. Indeed, yeah, in that case, you will have to have separate states that describe the dosing routes. So a very good question, but certainly something that we can extend. Yeah, another question I see from Vincent. So he asked, you mentioned that the integration of the new ODE is computationally performed using a forward Euler approach. Does that mean that this approach is limited to non-step problems? Yes, a very good question. So certainly in our current Wolfram language implementation, we have only done this for the case of forward Euler, and we know, of course, the limitations associated with this numerical integration scheme. So in this other Python approach, PyTorch-based approach, we are able to use other ODE solvers as well. Yeah, I think here, I think would be quite interesting to see within the Wolfram language if there can be ODE solvers that are based on neural network that we can utilize for stiff problems. And I think that would really make this approach amenable to many other problems where we see more stiffness. I think in this particular context, stiffness is not as much of an issue, but if you imagine you have multi-scale phenomena, phenomena occurring at cellular level versus at the in vivo level, that's a very a challenging problem to solve. Yeah, so thanks everyone for your attention. So, and appreciate any other inputs, so feel free to reach out if you have further questions that have not been addressed in the session. Appreciate your interest in our work.